So I thought today I would begin by going through a little bit of data and seeing how some of these codes work before we return to the proofs. So this data set that I'm going to play with, we'll see a few times during the course. It's the same as what you've been seeing in the problem sheets, but I'll talk to you a little bit about how this is constructed. Okay, here we go. So what I've done is, for the sake of having some real data to play with, I went on Project Gutenberg and I got 4 pieces of text that are open source, out of copyright, which means we can just use them. What have we got? We have the collected works of Shakespeare, the collected works of Walt Whitman, the collected works of Michel de Montaigne, translated into English, and the collected works of Mark Twain. So if we go through, here we are. And for those of you doing computer science type courses, I'm very sorry. I'm going to give code which is not optimized at all. It's meant to be quick and easy to read rather than doing anything too clever. Okay, so I've just read in all of this data. It's about 24 million characters. And I'm going to strip it down. So what this code I've just run does, it takes the code, converts everything to uppercase, and gets rid of all punctuation except spaces. So we have a 27-letter alphabet, A to Z, and a space, which I've replaced with an underscore so that it's easier to read. Okay, so we'll see that there's an underscore instead of a space. Okay, so let's have a look. Here we can go past. Where is it? What's it done now? Here it is. No, it has. There it is. So you can see the file begins the Project Gutenberg ebook of the complete works of William Shakespeare. This ebook is for blah, blah, blah. If I go to 5,000 to 5,100, thy summer ere thou be distilled, make sweet some vile treasure, etc., etc. So this is just Shakespeare written out in capital letters. There we are, and we've got 24 million characters of this stuff. Okay, which is hopefully enough that we can begin to learn something about how English works as a language. It's not enough that we can do any arguments. Well, we're not going to be able to train a large language model on this, but we'll be able to play with it and get something interesting. So what I do now is I'm going to strip out every occurrence of every combination of 1, 2, 3, or 4 characters. Okay, so just stripping out these counts. I'm not going to run this. It just takes a couple of minutes to run and then save them as CSVs. Okay, so if I do this, I can now move here. So what I'm doing is we're going to construct some codes. So let's begin with the single counts data. Oh, why is it that every time I try and do this live, something goes horribly wrong? It's because I haven't put where the data file is. There we go. Now it likes me. Never try and run code live in a lecture. It's a lesson that I'm yet to learn. So let's just see what this looks like. So this is a dictionary which lists out the letters, as you can see, and how many occurrences of each of those letters there are in our file. Okay, just for the single counts, that's all it does. And here's some code which will create the Shannon code, as we've discussed last lecture. So we're going to add a little bit of tolerance so that we can deal if there's ever a 0, it doesn't die. But we compute the probabilities just by taking those counts, saying we're going to randomly choose a letter from our text, therefore that's a good way of modeling the probability. So we calculate the counts divided by the total number, and that gives us probabilities of different letters. We then go through, if you remember, we construct the cumulative probability, which is the sum of the probabilities of the symbol that came before this symbol. And note that I have sorted them in the first step. I have sorted probabilities. Then I calculate the lengths of the that I want for my code words. This is by taking the log to base 2, rounding it up. Then I transmit my cumulative probabilities into binary. I do this using a bit of a hack, just add 1 and then extract the binary expansion of it. It's the fastest way I could find to do it. And then finally, construct the code words by cutting down to the relevant length. So there is my code to create the Shannon code. And if I do this, here we go. Here's the Shannon code. In order. So space is the most common character in our file. So it's coming out at 3 zeros in a row. Then E is 0011, T is 0100, etc. And you can just see it goes through and creates the Shannon code. Okay, using these sorted probabilities. And it's a bit boring, but you can see that Q and Z are quite long. They have strings of ones and then a 0, 1. You can also see this, it's clearly not optimal because Z does not have another code of the same length. So by the time I've gotten one step earlier for Z, I know that I've got a Z and I could just stop there. But the Shannon code doesn't take account of this. It's not optimized in the sense of being a canonical code. Okay, another example that we've had is the Huffman code. So here I'm constructing the Huffman code. So this goes through and basically creates the vector of all the probabilities, finds the two smallest things, joins them together and keep tracks that it has joined them together. So it finds the lowest index, the second lowest index, merges them, builds up code words sequentially from this, and then add all the code words together, paste everything together, and spit it out. Okay, so here we go. So now if I construct my codes, again you can see I have these codes. These have not been sorted. So now it's presenting them in A, B, C, D, E order, rather than shortest thing or highest probability thing first. Even so, you can see A is still length 4. If I go to the end, a space is now length 2 instead of length 3, as we had a moment ago. And a Z and Y's, you can see they're quite a bit shorter. But the Huffman code, we claimed, is optimal. So let's try and see if I calculate the average length. So this is the average number of symbols used to encode a single character chosen at random. Well, if I use the Shannon code, it's 4.55. So the length is on average 4.55 zeros and ones to encode a single character. If I use the Huffman, it's 4.1. So this is faster. Okay, well we can do more. So we can actually build an encoder and decoder for this code. So all this is going to do, the encoder goes through, takes the input, it finds, takes a block, so it uses the code we've just constructed. In this example, we use the code of length 1, so it's just going to work in a single term, finds that, constructs a message from it, pastes them all together and outputs it. You can go through this code yourself. I'll put all of this online. So the encoder, so if I look at the message, the rain in Spain, what does it look like? Well, under a Huffman coding, there is the message, the rain in Spain, encoded as a series of zeros and ones, encoded using a single character level encoding. So just for out of interest, if I looked at how these things are more naturally encoded using ASCII, so ASCII is a base, it's a 256 character alphabet. So these days we use normally UTF-8, it's a slightly nicer encoding. But if I go ASCII, there is the length of the message. It's much longer, but that's because ASCII contains all the punctuation marks, lowercase, uppercase, etc. So of course it's longer because it has more things it should be able to encode. We can build a decoder. Again, decoder just goes through, keeps eating one character at a time until it finds a code word. If it finds a code word, spits that out, starts again, eats one character at a time, spits it out. That's all the decoder is doing. So here we have it. And so if I take my Shannon coded message, encode it, decode it, and similarly Huffman coded. All right, that's fun, but let's try something a little bit more interesting. So if I now work with the double counts, so the double counts are not quite the block code. The block code that we've been talking about assumes IID. So that's where I took the single count data, pasted it together and used that. Here we're going to use the pairs. So I'm looking at real occurrences of pairs, which means their probabilities are not quite the product of two. That means, for example, space was a very common character, but two spaces, one after the other, never happens. So we're going to get different probabilities because of this. Okay, so let's construct our codes. So the Shannon code, here it is. So the most common sequence is E, then a space, or then space, then a T. And so we're encoding these pairs. Similarly, I can encode the Huffman using the Huffman code. There we are. If I compute the lengths have doubled because I'm now encoding two characters. But if I divided those by 2, you'd see that I'm actually doing something quite a bit shorter on average for two characters than the single character I had before. I'm getting that increase in efficiency. So I can encode a message. If I go down, I can try decoding my message. And you'll notice that when I've encoded the rain in Spain, I've had to add a space at the end because I'm encoding two characters at a time. So I need to have an even number of characters in the end when I go through this argument. This allows us also to demonstrate one of the problems. If I introduce an error into the encoded message with a Huffman code, what happens? Well, one of the problems is that error can cause me to lose phase. I end up moving to a different code word, but that propagates throughout, because remember, I go through the length of the code word, but I only know when a code word stops because I've seen a code word. So if there's an error, I introduce an error in the first character, that introduces errors in the second, third, fourth, etc. So if I introduce an error at point 1, I get complete garbage when I try and decode it. So it does successfully decode something, but it's complete nonsense, and it's not even nonsense that's fixed early on. It actually happens all the way through, and I never get back into phase with a Huffman code. And that's one of the big flaws of this approach. Okay, that's enough of that for now. Were there any questions about this? I'll put all the code online. It's simple Python. If not, I will close that and we can get back to proving some things. Okay, so where were we last time? We were looking at the Huffman code and we had this lemma about canonical codes, which we wrote out. So we had let P be a PMF on X 1 to M, and assume P1 greater than P2 greater than or equal to, etc., greater than or equal to Pm. So I've ordered these in a decreasing way. Then there exists an optimal prefix code and any optimal prefix code satisfies a few statements. 1, Pj greater than Pk implies Cxj is less than or equal to Cxk. So a more likely code word has a more likely input has a shorter, weakly shorter code word length. 2, there are 2 or more longest code words. So you can't have a unique longest code word. 3, 2 of the longest code words differ only in the last digit. And we call a code satisfying this a canonical code. So this last statement is really each longest code word comes with a partner and its partner and it only differ in the last place. So let's prove it. Okay, so the fact there exists an optimal prefix code we've already seen. So let's leave that done. Let's consider an optimal prefix code. So consider an optimal prefix code C and C prime defined by exchanging the code words for xj and xk for some jk with p k less than pj. So what I do is I take an optimal code word and I consider what happens if I just take two code words and swap them in the tree. So then, okay, I know that, well, C is optimal, so the sum over I, pi length C prime xi, the average length under C prime has to be more than the average length under C. Okay, that's just a statement of optimality. But these two codes differ only in one term. So cancelling everything that is the same, I get pj c xk plus pk c xj. So these are the two terms that I have switched if I look according to code word C prime. But code word C prime means that I use C of xk and C of xj because they're the opposites. And then I subtract off pj c xj minus pk c xk. Okay, so this is what the lengths according to the original code word. But this, of course, is just pj minus pk of c times c xk plus, minus c xj. And we notice that, well, this is positive, this is positive, so we need to know that this has to be positive as well. So c xk is greater than or equal to c xj. So the length of xk must be at least as big as xj when I've ordered by these probabilities. Okay, so that was point one. Point two, for two, assume the contrary and drop the last digit from the final code word, or the longest code word. So if there is a unique longest code word, then I can identify it and I can just drop the final digit from it. That makes it shorter. But if I do that, then, hang on, the result is still prefix, because it was a unique code word that I have, and the code was prefix. Drop the final digit, I've still got a uniquely defined object. Okay, so I still have a code word which uniquely corresponds to an input. It's still prefix, it has shorter code words and has shorter code words. So the original was not optimal. Okay, I should say here I'm going to add pi greater than 0 for all I, just to avoid trivialities. If you've got a 0 probability, you can make the code word according to it as long as you like. Wouldn't make any difference. So here I should say that I'm excluding trivial examples in this result. Okay, so now point 3. So for 3, identify a code word with a rooted tree. We've already seen how to do this, so you write out your code word as a tree, and then we notice as there's no longest code word, each of those, that last code word, a longest code word, has something that's in the same branch as it. So if you think, if I draw the picture here, if these two are longest, I can just switch them. So they differ only in the final digit. Okay, a code word of maximum length must have a sibling. Okay, CF2. So by 2, there's no longest code word, therefore it has a sibling. Therefore, I've got something that looks like this. Everyone happy? Yes.
In part 3, you said identify a code word with the rooted tree. So identify a code.
Yes, sorry, you are perfectly correct. Yeah. Okay, so now that we've got this result, we can prove the Huffman code is indeed optimal. So let's prove the optimality of the Huffman method. Okay, so proof. Fix a PMF P with P1 greater than or equal to P2 greater than or equal to PM. And again, I'm going to make it greater than 0 so that I don't have to mess around with trivialities. Okay, denote by P prime the PMF on m-1 symbols given by merging PM and PM minus 1. Happy with that? So I've taken all my symbols, and then I take the two that are least likely in whatever ordering I've got here. So some decreasing ordering, take the final two and merge them. And I call that P prime. Okay. i.e. Pi equals P prime I for I less than m minus 1. P prime m minus 1 equals Pm plus Pm minus 1. Okay, so now I'm just going to suppose, let Cp be a canonical optimal code for P, using this definition here. Okay, so once I've got a code for P, define C prime as the code for P prime given by merging the leaves for Pm minus 1 and Pm in the rooted tree representing Cp. So I'm assuming that I can order these in a way so that I have a rooted tree representing CP. I can then merge these final two. They are siblings, so I can merge them. Okay, so I'm assuming I can do this. So that defines C prime as the, if I'm staying with the notes, CP prime. So this is a code where I've ignored that final term. Merge those final two symbols. Okay. The difference in expected lengths is, so L, I'll use a capital L for the expected length. So length of CP minus the length CP prime is equal to P m minus 1 L plus Pm L minus P prime m minus 1 L minus 1, where L is the length of code word of m minus 1 under CP prime. Sorry, the CP, I should say. So this is the longest code word under CP. I get this calculation here. Okay, so this is just telling me if I ignored that final step, how much would I gain? Well, it's precisely this amount. On the other hand, so suppose now EP is obtained from CP prime. So what I'm going to do now is I'm going to take CP prime and I'm going to blow those last two symbols apart again. So if I do this, okay, I replace by replacing the leaf for P prime m minus 1 with a rooted tree with two leaves, Pm and Pm minus 1. Okay, these are the probabilities of the two leaves. So I'm now taking my constrained, blowing it up somehow, making it bigger. Okay, then I can compute the difference in code word lengths again. So the length of EP minus the length CP prime. Sorry, I've done this wrong. No! Let's do EP prime. EP prime. So I'm going to have to add something. I should have been more careful. Suppose EP prime is optimal for P prime. And that's better. So what I do now, okay, I've computed this. Now I say, let's start with something which we know is optimal for the smaller case. Expand the last leaf out. Okay, so now I can compare my code word lengths again. Well, the difference is just Pm minus 1 plus Pm. Okay, this was equal to Pm minus 1 minus Pm, plus Pm rather. Just simplifying this out. And I notice these two things are the same. Therefore, LEP minus LCP plus LCP prime minus LEP prime is equal to 0. Now, why have I done this slightly weird calculation? Well, the point is that I know by construction that CP is optimal. So we started with an optimal code. So EP might not be optimal, but I know therefore this term has to be positive. What about this? Well, I know that EP prime is optimal. CP prime might not be. So this also is positive. So I've got a positive number, and their sum is 0, therefore everything here is 0. Therefore, CP must be optimal, EP must be optimal, CP prime and EP prime must be optimal. Hence, what do we get? So EP is optimal for P. Okay, so what I've done is I've just shown that if I take any optimal code, EP prime, and I expand it by taking apart the two least likely terms, I get an optimal code. And the Huffman code is entirely constructed out of these types of actions. Take something, split it up, okay? Or take something and merge it, really, for the Huffman code. And so this argument shows us that the Huffman must be optimal. Okay. Yes. Sorry, yeah, that was EP prime. Yeah. Sorry, me just being thick. Okay. So the Huffman code's constructed using these operations, therefore Huffman is optimal. Okay, Huffman codes. They're optimal. That's great. So we use them a lot. We use them in lots of things. MP3s use them, zip type formats use them, JPEG uses them. What you actually do in practice is often a little bit more nuanced because, as you'll see in the example, we have two problems with Huffman codes. One, I've got to estimate the probabilities. And two, I worry that I might fall out of phase if I introduce a single error. So there are extensions of this which are used more commonly than the Huffman algorithm itself. But if you go and you look in most of if you try and zip something on your computer, if you do this with a higher-powered piece of software than Windows normally would give you, you can actually specify the encoding, and Huffman is usually one of the examples. Okay, now, not all optimal codes are Huffman. So a simple example of a Huffman code of a code that is optimal but is not Huffman. Let's take so P, probability of X. We'll do a simple example: 0.3, 0.3, 0.2, 0.2. So X, 1, 2, 3, 4. So what would the Huffman algorithm do? Well, you go 3, 4, join them together, and then you join in, I don't know, 1, and then you join in 2. And I could choose to do the 1 and the 2 in the other order, but otherwise all the Huffman codes will look like this. Now we can compute the average length in that example. So it's length 3, 3, 2, 1, which averages out at 2. Yes? Hang on, let me think. Yes, you're right, sorry. There you are. 1 and 2. Okay. Oh, that makes it even easier. So they're 2, 2, 2, and 2. So clearly the average length is 2. Okay? But now, as soon as you see that, it means I could permute these things. And the fact that 3 and 4 differ only in the last digit doesn't really matter. If I order these things in a different way, I'm still going to get exactly length 2. So I could look at the code 0, 1, 0, 0, 1, 1, 1, 0. That code cannot be Huffman because you'll see 3 and 4 don't differ in the last digit. So there's no Huffman construction that would ever produce this code, but it is indeed optimal because it's got the same code word lengths as a Huffman code. In practice, what happens? Well, you have to know P, you have to estimate P somehow. You need to construct the full code book. Constructing the code book takes time. You have to store the code book. You need to put it somewhere. So in terms of the length of a message, if you've got to communicate the code book, that's expensive. And you can't just reconstruct it because Huffman doesn't give you a unique way of building this out. Now, optimality, what can we say about the optimality? Well, Huffman is optimal. That means, well, I know h of x less than or equal to the expected code word length, which is less than h x plus 1, but I can't say much more than that. What I can say, as always, I could apply the Huffman algorithm to blocks. If I had an IID sequence, I'd now apply the Huffman algorithm to blocks. That gives me a way of doing this, and you remember that you get a 1 over n type behavior. Sounds great. Except now there's even more things I have to store and remember and communicate in order to store my Huffman code. So that is one of the main challenges. Okay, so what else can be done? This brings us to another code called Elias's code. So Elias's code is very similar to the Shannon code that we saw, except we're not going to order the probabilities, which sounds like a trivial change, but it actually allows us to do some rather cool things with it. Elias never published his work. It's known in the literature, it's associated with him, but apparently was never published. So what do we do? Okay, if we remember the Shannon construction, what we have is we take the unit interval and we split this thing up according to intervals with the size of the probability. So in Elias's code, we're going to do the same thing. So associate symbol xi with the real number. Okay, sum I less than r pi plus pr over 2 with pi's unsorted. So what's happening here? So I've got, let's just do an example. So x can be 0, 1, 2, 3, 4. Sorry, we've been starting counting at 1 in this course. So 1, 2, 3, 4, 5. And we'll give ourselves the probability 0.3, 0.1, 0.2, 0.1, 2, 7, 0.3. There we go. So what's that look like? 0, 3, 1, 2, 2, 1, 3. That'll do. A little bit smaller, and we'll move that slightly over there. So this is 1, 2, 3, 4, 5. There's our real line. So what I'm going to do, I'm going to take each of these intervals and I'm going to pick their midpoints. So this is going to be R1, this is going to be R2, this is going to be R3, R4, and R5. And that's all this formula does. This identifies the midpoint. Sorry, this should be j less than I, and let's call that j, let's call that I, and we'll call this Ri. There's better notation. So what I've done, I've just taken my probabilities, taken the real line, and I've associated each symbol with the midpoint of this interval. Okay, so how far apart are these symbols? Well, what we can see, when we were looking at the Shannon code, we knew that we had ordered our probabilities. That allowed us to guarantee if I tell you this point, I've got at least this much distance until the next code word. In the Shannon code, it's the length of that interval on the left. And on the right, we would have an even longer interval. Here, what do we know? Well, we know that the distance between R1 and R2 is here. Okay, that's a distance. And in theory, you could imagine I could change the probabilities to make 2 as small as I like. And so what I can really guarantee is that the distance between R1 and the next code word is at least that long. And similarly on the left-hand side. So on the left and on the right, I know I've got at least half that interval length. So what do I need to do to tell you which code word I have? I need to tell you this number sufficiently accurately that you can figure out what number I'm telling you within that much tolerance. Okay, so if I can tell you a number, if I tell you that my number is 0.21, if I tell you that it's 0.21, you know that lies in this interval. It's slightly to the right, but it's accurate enough that you can tell that it isn't this number over here. Okay, it's somewhere in this interval, and that's what I'm trying to tell you. So I'm going to communicate to you a number in this interval accurately enough that you know I'm in that interval. How do I do that? Well, I'm going to do the basic trick. Okay, so observe each Ri differs from every other by at least pi over 2. So that's the distance. I can guarantee that distance. So if we communicate, okay, so I'm going to take minus log pi over 2, take the ceiling and add 1. That's enough digits to make sure that I have communicated. Sorry, if I communicate that many digits, then you're able to tell exactly where we are. So if I communicate this many binary digits, we can identify Ri. Now this, of course, is equal to the ceiling of minus log pi plus 1. And so you can see the difference is now that I've added this 1. That's the key thing. And I'm transmitting one more digit for this code word. So what do I do? So we communicate this many digits of the binary expansion of the number r. That is enough to identify the code word. So the code word for xi is the first log pi plus 1 digits of ri. And that is Elias's code. Okay. Well, I've transmitted one more digit than the Shannon code. So by the same calculation as above, as before, you can see that Elias's code satisfies h of x plus 1 is less than or equal to the expected code word length is less than h of x plus 2. And you go, that seems like a bad trade because I've got something which is actually worse than the optimal bound. Now, okay, does this matter? Well, there's one big advantage here. I don't have to tell you, I never have to communicate how I've constructed the code. The only thing I have to tell you is the probabilities. If I tell you the probabilities, the code is uniquely defined because I'm not having to order them in any way. I just tell you the probabilities in order and you can construct the code yourself. So that's one big advantage. We will see also that this allows us to construct the more general arithmetic codes. So what's an arithmetic code? It's Elias's code applied to blocks. So okay, so if I apply Elias's code to a block, that seems easy enough to understand. These have been discovered multiple times, so I'm not going to say who did them. They were constructed really in the 70s. And I'll draw a picture to tell you a bit of a story of how these work. Okay, so I could just write out all the probabilities and then construct the arithmetic code. What would that look like? Let's suppose for a moment that I had x being 1 and 2 with probabilities 0.6 and 0.4. Keep life very simple. Okay, so if I now looked at a block code, I would get the sequences 1, 1 with probability 0.36, 2, 2 with probability 0.16, 1, 2, and 2, 2 with probability 6 times 4. This is bad. What's 6 times 4? 0.24. I never claimed to be able to do arithmetic. Okay, so if I drew this out, what would I get? I would get the rather boring separation of the interval in this way. 0.6, 0.4. Now if I did this, what would I get? I would get 0.36, 0.24, 0.24, 0.16. Okay? And what you should notice is that this interval here looks the same as that interval there stretched. And so I could think of constructing this as a block code, going through, write out all the blocks, write out all their probabilities, build the arithmetic code from the probabilities. Okay, that's one way I can think about it, one way I can analyze it. Or I could think about, well, I'm going to take my interval, find the first value, figure out what interval I'm in, split that interval to get the next value, and repeat. Now the advantage of this is I don't have to construct the entire code book. I can say I can construct the code if I give you a particular input. Let's say 1, 2, 2, 1, 2. What do I need to do to construct this? Well, instead of writing out all the probabilities, I go 1. So that gives me, so this gets split up. So I'm going to draw it a little bit differently. So zoom out to here. 2. Okay, splitting this bit up. And then 2. And then 1. Okay, and so now I communicate this point here. And all I have to do is map that back through these transformations. So this point here is that point there, is that point there, is that point there, is that point there. And so I can just construct it this way. So if I can go through this and I can find this point, I don't need to construct the code word for any other input when I'm doing the encoding. Now, I've done this only at the level of waving my hands. I haven't actually done the construction. But this allows me to do this without writing down the code book. Yes?
So why are we having
So my code word is 1, 2, 2, 1. That's the input. Hang on. 1, 2, 2, 1. Have I done one too many steps? Okay, 1. There. Okay, so I've done 1, 2, 2, 1, 1. So now I'm going to take this point and I just map it back through, and that defines the real number. So arithmetic codes are very, very cool because you can do this. There's one dangerous fact, which we'll discuss more next time, which is you need very, very precise arithmetic to be able to do it. So the main problem here is figuring out how can you implement this practically with only finite precision arithmetic. We will talk more about that tomorrow.